In this example, I'm going to take a look at an object that was within the focal point of a concave mirror. So I'm going to put the focal point right here, and the focal point for this example is going to be 3 centimeters. And for this example, I'm going to place the object, DO, within the focal point. In the previous example, I did outside the focal point. In this example, I'm going to have it within the focal point. So here's my arrow that represents some object right there. And this is DO. And I'm going to write D over here. DO is going to be 1.5 centimeters, so halfway to the mirror. Remember again, all distances are measured relative to the mirror itself. So this distance from this point to the mirror is 3 centimeters. This distance from this point to the mirror is 3 centimeters. Excuse me, 1.5 centimeters. So we're going to find two things. A, we're going to draw the ray diagram so we can locate the image qualitatively. So ray diagram. And then secondly, we're going to find, so ray diagram. And then B, we're going to find DI using the mirror equation quantitatively. So let's take a look at the ray diagram first. So a light ray comes in, hits the top of this arrow, and one of those will reflect it parallel to the axis here. And we know that that light ray, when it reflects, goes to the focal point right about there. It's a little off. Right about here. Goes to the focal point. Right there. Okay. Another light ray hits it. The tip of this arrow hits the center of the mirror and reflects at the same exact angle. So I'll draw it down here like this. And if you notice, these two light rays, if I extend these, will never meet. They're going to diverge. These two are going to go off and never intersect. So what I can do is I can trace back where they behind the mirror. So this line, the reflected light ray, if I trace it back here, and I trace back this one, those extended light rays do meet. They meet behind the mirror. And the image they form is actually larger, and it's upright. And that's what your eye would see. Your eye, if you stood here, your brain would see that these light rays come from an object that appears to be here. It's called a virtual image, because it's not really there. It's what your mind perceives to be there. In the previous example, the two light rays met on the same side of the mirror, and it was a real image. You could project that on a screen. So there's the ray diagram. One ray that's parallel to the principal axis, and one that hits the mirror at the principal axis, reflects off at the same angle. We trace them back. So for the quantitative part, we have step 1. Again, label these, number these 1, 2, and 3. Here you have the mirror equation, 1 over f equals 1 over di plus 1 over do. Step 2, I'm going to list the variables. So I have focal length, I have di and do. The focal length is given, it's 3 centimeters. Make sure to put your units there, 3 centimeters. The di we don't know, so I put a box. And the d object we said is going to be at 1.5 centimeters. So those are my variables. And then lastly, we do the solve part. So the solve part, we're going to have, I break it into 5 sub-steps. Again, just so we make sure we're clear on all the steps. So I say 1 over f is equal to 1 over di plus 1 over do. Second sub-step is going to be 1 over 3, 1 over di, because we're trying to find di, plus 1 over 1.5. So I just plug the numbers in there. The third sub-step, I'm going to solve for di. So if I bring 1 over di is equal to, I'm going to bring this term over to the other side of the equation, so it's 1 over 3 minus 1 over 1.5. And if I do the math there, 1 over di is equal to, this is 0.33 minus 1 over 0.15 is 0.667, repeating like that, which is equal to negative 0.33, negative 0.33, because there's a larger value and it's negative, which is interesting because our DI, if we cross multiply, is going to be 1 over negative 0.33, which is equal to negative 3 centimeters. So we get a negative answer here, which is interesting. What the negative represents, box your answer here. So this distance right here is about 3 centimeters. It's interesting because it's the same distance away. But it's negative, meaning it's on the other side of the mirror. Negative meaning virtual. So if you get a negative sign here from the math, that tells you that your image is a virtual image. And if you look at the ray diagram, it actually is. It's on the other side of the mirror. So it's not really there. It's what your eye or brain perceives to be there. So this is an example where we do a ray diagram and solve for the DI for an object when it's within the focal point versus outside the focal point of a concave mirror.